So welcome back to Origin Seminar. And today's speakers, Anjali, Piette, and Tanya Pai will introduce Anjali today.
Yeah, thank you. Thank you, Serena, and thank you all for coming to talk. It's my pleasure to introduce Anjali, Piette. Many of you already met Anjali. For those of you who haven't, Anjali has received her master's and bachelor from Cambridge University, and she also did her PhD there, where on the topic of thermal and radiative properties of exoplanet atmospheres across the mass range. And that is a key point there. Anjali has an exceptionally broad scope of research, where her work includes everything from brown dwarfs through hot Jupiters, all the way down to sub-Neptunes and even lava planets. So I'm very excited to hear her presentation about these. I will just mention that currently she's for 2 more weeks a Carnegie postdoctoral fellow at the Earth and Planets Laboratory in Washington, D.C. And in 2 weeks from now, she will be moving on to Birmingham as a faculty member, where she will extend her work. So, Anjali, the floor is yours.
Thank you so much. Yeah, thank you so much for having me. I'm really looking forward to chatting with many of you today and tomorrow as well. Yeah, it's really a pleasure to be here and to talk to you. So yeah, as Daniel said, I like to think about planets of all sizes, but today I'm going to focus specifically on sub-Neptunes, which is something I've been really excited about lately. I should use the... There we go. Okay. So yeah, I like to think about all these planets, and I really like to start off these talks by looking at the diversity of the exoplanet population as a whole, or at least for transiting planets. And of course, we have everything from giant planets and hot Jupiters all the way down to terrestrials. But something that always really jumps out to me in this figure is the sub-Neptunes, between the sizes of Earth and Neptune, which are so abundant, and I think raise many questions about how they formed. And really, the way I like to think about the exoplanet population is to see this the series of different experiments, different planets in this population can help us to isolate different regimes of planetary physics and learn more about those, and hopefully piece together how all these planets behave. And in particular, I think some of the questions that stand out to me in the field at the moment are how these many different types of planets form and evolve. What the diversity of their interior compositions, could we be looking at water worlds in here, or diverse rocky compositions as well? And also, what is the diversity of their climates and their atmospheres? And of course, all 3 of these questions fundamentally are really important to answering questions like, are there other habitable planets out there, and what would they look like? So as I mentioned, I'm going to focus specifically on the sub-Neptunes here, between the sizes of Earth and Neptune, and to see how we can answer some of these questions, particularly for this regime. And just as a little outline for this talk, I'm going to start off just by talking about what we know already about sub-Neptunes, what we can continue to learn about them with JWST. Then I'm going to talk more about how we can start to probe the surfaces of some of these sub-Neptunes using lava worlds specifically. Then I'm going to go to a slightly larger sub-Neptune, GJ1214b, which is going to be hazy, which we've observed recently with JWST. I'll talk about what we've learned from those observations. And finally, I'll just finish off by talking about what I'm really excited about in the sub-Neptune regime in the years to come. So first of all, with sub-Neptunes, I'm sure many of you have seen this figure before. We know that we could start learning about sub-Neptunes, even just looking at the distribution of their radii and those demographics. And of course, this is a bimodal distribution. I'm just going to label the smaller peak here as super-Earths, and a slightly larger peak as mini-Neptunes. And of course, what's really interesting about this bimodality is the fact that it exists not only in the radius space, but in the joint radius and period space, which tells us something about how these planets might have formed and evolved. For example, this distribution could be a result of atmospheric escape processes. If, for example, both the super-Earths and the sub-Neptunes formed with thick hydrogen-rich atmospheres, but the super-Earths, being slightly closer to their host stars, perhaps slightly lower mass, lost those atmospheres more readily, leaving behind smaller cores, whereas the larger mini-Neptunes were able to hold on to those thicker atmospheres. There are other theories as well, including super-Earths forming in a more gas-poor environment, and realistically, I think we're probably looking at some superposition of these different explanations. Okay, so that was radius and period, but another dimension that really that I find interesting is adding mass to the picture. So here I'm showing a mass radius diagram with a few known sub-Neptunes plotted on here. And just to guide the eye, I've also plotted some mass radius curves for some fixed interior compositions. So the grey one at the bottom here is for an Earth-like interior with an iron core and a silicate mantle. Then in purple, this is for 100% silicate interior, the pure rock. And the blue dashed line is for 100% water planet. This is dashed because it's very temperature sensitive, so this is for 300 Kelvin, but it gives us a rough idea. So we can already sort of get some broad ideas about the different compositions of the interiors and atmospheres of some of these planets. For example, way up here, for the planets that are much less dense than a pure water world, we know that there has to be a lower density component in the form of a hydrogen-rich atmosphere. On the other end of the scale, anything which is denser than an Earth-like composition needs something, for example, like enhanced iron in that interior to increase its bulk density. But the region that I find very exciting at the moment is the one that I've highlighted here, blue, where these planets are less dense than an Earth-like composition. So something different is going on here. This does not look like our own Earth. But at the same time, these aren't so low density that you require a hydrogen-rich atmosphere. There are several different explanations for these sort of intermediate bulk densities. One of those, of course, is volatile-rich interiors. For example, water worlds. We could be looking at a few planets with global, very thick water oceans, whether liquid or supercritical. We can also have volatile-rich interiors in other senses. For example, you can fit a lot of volatiles like hydrogen and oxygen and carbon in an iron core and reduce its bulk density. Some of these planets could just be very iron poor. That would reduce their bulk density a bit. And for some of these sub-Neptunes in this blue region, especially the cooler ones, they could have very thin hydrogen-rich atmospheres. Though as we go to the hotter end of the scale, it becomes more difficult to hold on to those atmospheres if they're primordial. So already mass, radius, and orbital period give us this insight into the possibility of the diversity of the sub-Neptunes. But I think a really critical piece of the puzzle that we need to add to that is what we can learn from the atmosphere. So the reason for that is that the atmosphere gives us, first of all, really crucial compositional information, and also a lot of information about the energetic conditions of the planet. So just as some examples, if we consider a sub-Neptune, perhaps a super-Earth that has a surface boundary, we can imagine surface outgassing or ingassing, which will affect the composition of that atmosphere. And we can go and observe that atmosphere and be sensitive to those interactions. We can also have energy transport from the day to the night side, or vertically as well in the atmosphere, which are sensitive to clouds and hazes as well. Can increase the bond albedo, cool the whole planet, or can also have spectral features which we can measure. So we can have a probe with the condensates in these atmospheres. And by putting all of these together, we can learn more about what the interior composition is by looking at the atmosphere. So since I'm going to talk more about atmospheric observations, I just wanted to have a very quick introduction for anyone who that might be useful for. Obviously, the most prolific method that's been used to observe the atmospheres of transiting exoplanets has been transmission spectroscopy, where the planet is passing in front of the star and we see light from the star passing through the limb of the atmosphere. But I'm mostly going to focus actually on emission spectroscopy, either in secondary eclipse or also full phase curves where we can see the emission, not only from the day side, but also other phases, including the night side. So what do we actually get from these atmospheric observations? This is just a model secondary eclipse spectrum for the day side of a made-up planet. And there's a lot of information in a data set like this. I should add that these aren't data points, but relatively medium resolution model, and the error bars vary a lot with the target, and I'll be showing more of those later. So one thing we can start to measure is the chemistry of the atmosphere through spectral features that we see. So for example, in this case, CO2 and also water vapor. If our signal to noise is good enough, we can also measure chemical abundances for those species, and not only their presence, and also relative abundances of different species. We can also learn about the energy budget of the atmosphere. Especially in emission spectroscopy, we're very sensitive to the temperature of the day side. And so if there's energy being transported from the day side to the night side, or being reflected into space, for example, by clouds and hazes, we see that as a cooling of the day side, which we are then sensitive to. On top of that, we're very sensitive to the vertical temperature gradient in the atmosphere. I'm going to come back to this later on. But effectively, the steeper your temperature gradient vertically, the deeper these spectral features will be. And so we can have some idea of that kind of energy transport. And also, as I briefly mentioned, we can be sensitive to things like clouds and hazes, which not only increase reflection of the atmosphere on the day side, but in some cases we can even get spectral features from those as well. And the way that we can back out all the information from these data sets is by considering all the physics that goes in there, including things like the opacity of the atmosphere, the chemical composition, radiative transfer, radiative convective equilibrium, and also 3D effects, which are shaping those temperature gradients, both vertical and horizontal, and the eventual spectrum which comes out of the top and which will be then observed. So I've been talking more about models and the theory of this, but JWST has really provided a revolution in observing these sub-Neptunes. And just as some examples, this here is a measured spectrum for this one's the night side of TJ1240b, which I'm going to talk about later. This is the transmission spectrum for K218b, where we've detected methane and CO2. And this is another spectrum for TJ486, which Sarah led. And so these data sets are really rolling in, and they're allowing us to probe this sub-Neptune regime. But the question is, what can we learn from them? What is the information that we can get out from these data sets? And what does that mean, not only for the atmospheres of these planets, but for their interiors and their formation and evolution as well? So now I'm going to move on to specifically what we can learn about the surface compositions of some of these sub-Neptunes. And just coming a little bit closer to home to begin with, we know that on the Earth and in the solar system, we can start to learn about the interiors of planets and moons by looking at processes like volcanism, where we have chemical exchange between the atmosphere and the interior. And we can learn a lot from these processes. It's more difficult to dig down, but if we have gases coming out, that really helps to interpret those reactions. And we can try to do something similar in the context of exoplanets as well. But since those planets are a little bit further away, it helps to really wrap things up and go to an extreme form of this kind of interaction. And what I mean by that is specifically to look at lava worlds, or planets that are so close to their host star that they are hot enough to melt rock and any other volatiles there as well, so that whatever is the composition at the surface, that's going to evaporate into the atmosphere. And when we probe that atmosphere, we're actually probing the surface composition as well. And there are actually many known lava worlds which we can go and observe, which have already started to be observed with JWST. And these have dayside temperatures even exceeding 2000 Kelvin, which ensures that we're vaporizing all of that surface material on the dayside. And some of these lava worlds are consistent with an Earth-like interior composition. So for example, ones like K214b here, which is very likely a rocky planet with a rocky mantle, just with a rock vapor atmosphere because it's so hot. But I want to draw your attention back to this blue shaded region that I alluded to earlier, where these are planets that are less dense than an Earth-like composition, and we're interested in knowing if they could have volatiles in their interiors. And so there are several ultra-hot super-Earths in this regime, these lava worlds, like 55 Cancun E, H316-7b, 2I561b, and a few others as well. And so the question we can start to ask those planets is not only what is the rock vapor evaporating from their surfaces, but are there volatiles evaporating from their surfaces as well? And could that tell us about the presence of volatile-rich interiors in the super-Earth population? So just to clarify that, what I mean is that if we have a purely rocky surface, then we would expect a pure rock vapor atmosphere to evaporate from that. And so if we look at one of these low density lava worlds and we see just rock vapor, that might mean that its low bulk density is not coming from volatiles in the mantle. Maybe it's coming from volatiles in the core, or because it's iron core. But on the other hand, if we consider the hypothesis that these planets have a lot of volatiles in their mantles, then if we have this combination of rocky and volatile material at the surface, that should evaporate to a mixed rock vapor and volatile vapor atmosphere as well. And we can try to distinguish these two different scenarios with observations, for example, with JWST. And I just want to quickly note what I mean when we can combine these rocky material and volatiles in the interior. A classical picture of that is having volatiles dissolved in the magma ocean or even in the solid mantle. In that case, the amount of volatiles we can fit in there is limited by the solubility in either the magma ocean or the solid mantle. On the other hand, as we go to very high temperatures and pressures, especially the supercritical regime, we can actually get water rock miscibility, in which case you can fit an arbitrary amount of water into a rocky mantle, for example. And because some of these lava worlds reach really, really high temperatures, sort of 3000 Kelvin and hotter, this miscibility regime is potentially accessible, actually, for some of these targets. And these planets could potentially fit a very large amount of water vapor into their mantles, or water drop vapor. Okay, so if we have this mixed rocky and volatile surface, we expect it to evaporate into the atmosphere, into a mixed rock vapor and volatile atmosphere, as I mentioned. And so the questions that I have about this mixed composition atmosphere is, first of all, what is the resulting chemical composition when you mix those different components together? And what is the resulting opacity structure of the atmosphere? Secondly, what is the thermal structure of the atmosphere? What do those temperature gradients look like vertically? And finally, what are the volatile species that are detectable with JWST with a reasonable amount of observing time? And probably this last question sounds like the most interesting one, probably is. But I want to convince you that these first two questions are actually precursors to understanding this observability. To do that, I like to use this figure, which is actually for a hot Jupiter, but it illustrates this very nicely. So we know that in an atmosphere, if the opacity is really dominated by the optical and the UV, so things like sodium, potassium, SiO, then that leads to a thermal inversion in the atmosphere. So that would be this red temperature profile, where temperature increases as you go further up. And on the other hand, if your atmosphere is dominated by infrared opacity instead, from things like water vapor or CO2, the opposite happens, and we have a non-inversion in the atmosphere, shown here in blue. But what's the consequence of that on the spectrum? Well, if we have a thermal inversion, red, this corresponding red spectrum has emission bumps in the emission spectrum, whereas with a non-inversion, we get absorption features instead. Both of those are great. We can go and look for either emission or absorption features. The problem arises if we have an in-between scenario where the optical and UV opacity balances the infrared opacity just right, in which case we can get a relatively isothermal temperature profile, and the resulting spectrum is this gray one, which is just a black line. So we still get a temperature out of that. It's not the end of the world, but we're not getting spectral features from the chemistry in this isothermal scenario. So for these very extreme lava worlds with optical and UV opacity sources from the rock vapor and infrared opacity sources from the volatiles, what is the situation going to be, and will we be able to detect these features? So let's start off by looking at these different opacity sources. Here I'm showing absorption cross-sections for different chemical species in the atmosphere, weighted by their abundances. On the left, I'm showing this for a pure rock vapor atmosphere, and going to the right, this is adding more and more volatiles. So here we can see when there's only rock vapor in the atmosphere, the opacity is really dominated at the blue end, the UV and the optical, with very significant contributions from things like SiO, MgO, TiO, atomic iron, things like that. We have very little, relatively speaking, opacity in the infrared. But as we add volatiles like water vapor and CO2, the infrared opacity really jumps up and becomes very significant. And it has the power to reverse that gradient in the atmosphere. I'll also note that when we combine the rock vapor species and the volatiles, we get some interesting compounds like sodium hydroxide and potassium hydroxide, which also contribute in the infrared here. Okay, so I've showed there some mixtures of rocky material and volatiles. There are actually a lot of different unconstrained factors that affect the relative abundances of these different components. For example, how quickly is material being replenished at the surface to then be evaporated? How are different phases partitioned between the atmosphere and the interior? For example, water vapor is very soluble in magma oceans, so does it end up more in the atmosphere or more in the magma ocean? And then, of course, atmospheric escape is a very important factor in these highly irradiated planets. So we can ask, what is the rate of atmospheric escape? And in particular, are those rates different for different elements in the atmosphere? And can that fractionate the abundances that we see? But in this work, I'm going to simplify things and just marginalize over these different factors by modeling the atmosphere for a range of different compositions. And in particular, I looked at two sort of dimensions in chemistry. One being the ratio of rock vapor to volatile vapor in the atmosphere, all the way from a pure rock vapor atmosphere all the way to a volatile dominated one. And the second dimension is the composition of those volatiles. So either a pure H2O composition just for the volatiles, like a classic water world, or a combination of water vapor and CO2, if we assume that there's some carbon in there as well. And finally, a third scenario, which is similar to the water plus CO2, but I'm assuming that hydrogen has been lost to space. So it's a desiccated scenario which leaves behind only O2 and CO2 in the atmosphere. So we're going to test how those different compositions can affect the observability of volatiles in these lava world atmospheres. To do that, we have this coupled model which takes the volatile composition, the rock vapor composition, which is calculated using magma ocean outgassing code, vapor rock. With those combinations of elements, we then calculate equilibrium chemistry as a function of altitude and the atmosphere, and that is coupled self-consistently with the calculation of the temperature profile in radiative equilibrium, and that gives us a model emission spectrum for that case. I'm going to show you some of those model emission spectra with various features in them, but a really important question is, are those features large enough to be observed and detected with JWST? And so for that, I'm going to simulate some JWST observations, which I'll show you. But even further than that, even if we can see a little blip in our data, is it statistically significant? Can we really learn something about the composition of that atmosphere? So the next step is to then do mock inverse modeling or mock retrievals on the simulated JWST observations to see, would we be able to detect things like water vapor or CO2 in these atmospheres, but with statistical significance, so that we know which targets to go for. Okay, so another dimension which is really important here is temperature. We're talking about lava worlds very generally, but they're not all the same. And so I'm going to talk about a couple of different case studies. The hottest one being 55 Cancri E, which has a substellar temperature of about 2800 Kelvin. The other one is HD 3167b, a little bit cooler at 2500 Kelvin. And the coolest one is HD 86226c at about 1900 Kelvin. And we'll see how that affects the spectra. And the question here is specifically, how does the composition of these atmospheres and how do their temperatures affect their observable emission spectra and the chemistry which we can detect? Okay, so just to orient us on these figures that I'm going to be showing, on the left, these are temperature profiles for the atmosphere from these models. On the right are the corresponding emission spectra with matching colors. In the dark blue here, this is for the pure rock vapor atmosphere. And we can see here a thermal inversion in the atmosphere is getting hotter as we go higher. And in the corresponding emission spectrum, we see emission bumps here due to silicates in the mid-infrared. So that makes sense. We expect that from the very high UV and optical opacity for that case. But as we add more and more volatiles, getting more orange and yellow, we find that this temperature gradient flips from being thermally inverted to being non-inverted. And we start to get these absorption features from the volatiles. And the more volatiles we add, the deeper these features are. Something else I'd like to note here is that in the mid-infrared, in the purely rocky case, we have these silicate features. But when we add water vapor to the atmosphere, the water vapor opacity in the mid-infrared completely washes out these silicates. So that could potentially be a diagnostic as well, where if you see the silicates, maybe that means you don't have very much water vapor, if any. So what happens if we don't include water vapor in the atmosphere, if we have that desiccated scenario with just O2 and CO2? This changes things because water vapor contributes a lot of infrared opacity to the atmosphere. So if it's missing, we actually need more of the other volatiles like CO2 to make up for that missing infrared opacity. And so what we find is you need to add a higher percentage of volatiles in the atmosphere to start to get these deeper absorption features. And when you have a smaller fraction of volatiles, you can actually get emission features from the volatiles as well. But the silicate features here remain present for all of the different volatile fractions because there's no water vapor here to mask them out. However, the size of this feature is potentially challenging to detect. So then I also want to look at the effect of temperature here. On the left, I'm showing the case for HD3167b at about 2500 Kelvin, and on the right, the slightly hotter case at 2800 Kelvin. And the difference between these two is that in the hotter scenario, we are thermally dissociating some of the volatiles, especially water vapor. So that is removing infrared opacity from the atmosphere. And the effect is that we need more volatiles in the atmosphere in order to produce these absorption features. So the slightly cooler case, 10% of volatiles in the atmosphere is enough to start to form these absorption features. But for the hotter case, 55 Cancri E needs 70 to 90% of volatiles in the atmosphere to even get these absorption features. Another way of saying that is if we detect absorption features from CO2, for example, in the atmosphere of 55 Cancri E, that implies a high fraction of volatiles in its atmosphere to be able to even have this deep feature there. And there are observations that aren't published yet for JWST of 55 Cancri E that I think are coming soon, so that'll be really exciting to see. Okay, so the next thing that I promised is to see are these features detectable with statistical significance. So to do that, simulating observations using Pandexo, performing simulated retrievals on those observations, mock observations, and then using those retrievals to check the detection significance of water vapor and CO2. And so the short answer is that volatiles can be detectable with JWST in a very reasonable amount of observing time. It does depend on the amount of volatiles in the atmosphere, but for this best case scenario with 99% volatiles here, we have these nice features from CO2 and the combination of water and CO2 here. Here I've just shown one example of H23167b, but it's actually similar for the other case studies as well. And actually the error bars, if we consider 5 secondary eclipses, we can actually resolve these features nicely enough so that we can detect water and CO2 at around 3 sigma or better for all 3 of these targets. And for 55 Cancri E, we did this test specifically for the observations that were taken in cycle 1. And so it'll be very interesting to see what those turn out to look like and whether anything has been detected. So as I mentioned, 55 Cancri E has already been observed in cycle 1. That's coming soon. But there are also other targets coming too. And we can see that these lava worlds span a range of masses and bulk densities, different radii here. And so we can start to probe their interior compositions as a function of these different parameters. Another really interesting target that we'll be looking at in cycle 2 later this year is TY561b, which if I go back here, just there, it has a dayside of around 3000 Kelvin, consistent with having a volatile-rich interior based on its bulk density, but it also has a very interesting star. It's a thick-disk star enriched in alpha elements. And so something we can start to think about is, among these lava worlds, do we see trends in the presence of volatiles, varying with the stellar composition? Do stars with more oxygen result in more volatile-rich planets, for example? And so I already mentioned 55 Cancri E, TY561b, and these are some other lava worlds that are being observed in cycles 1 and 2. And so I hope that we can start to build up this sample to test the presence of volatiles as a function of these different parameters, specifically looking at, do we just see a pure rock vapor atmosphere, or do we detect the presence of volatiles as a function of mass, bulk density, and stellar properties? And then hopefully over time, as we build up this sample, we can start to characterize comparatively the sort of surface processes, surface interior compositions of these lava worlds in a similar way as what we can do in the solar system now. Okay, so that was sub-Neptune surfaces. I'm going to move on now to the hazy planet GJ1240b. And as I'm sure many of you know already, GJ1240b has really captured the interest and maybe frustrated a lot of people as well over the past decade. It's a really interesting target because its atmosphere, in theory, is very observable. This is the emission spectroscopy metric of how easy this planet is to observe with secondary eclipse spectroscopy, and it really stands out among other sub-Neptunes. Another really intriguing property is that its mass and radius are consistent with the degenerate solutions for the interior. So it could have a hydrogen-rich atmosphere with a denser core in the middle, but it could also have a substantial hydrosphere as well. Both of these options could satisfy the mass and radius measurements. So some of the questions we might have are, is GJ1214b a water world? Or is it, does it have a hydrogen-rich atmosphere that has been sculpted over time by atmospheric loss? For example, the loss of hydrogen over time could result in a higher metallicity in the atmosphere. And also, what is the interior composition beneath the atmosphere, whether it's steam-rich or hydrogen-rich? And so in the past, because it's such an interesting target, it has been observed very extensively, including with HST, and it resulted in the most famous / most expensive flat line in exoplanet science, as people say. And the really interesting thing about this flat transmission spectrum is that it implies the presence of clouds and or hazes in the atmosphere of GJ1240b. That's really interesting. That's a very exciting result in itself, but it does mean that we didn't get any information about the gas phase composition of this atmosphere because it was blocked by the clouds and hazes. So those previous HST observations and with other instruments were observed in transmission geometry, but I've been part of a team that has re-observed GJ1240b with JWST, but this time we observed a full phase curve, including the emission from the day side, from the night side, the phases in between, and as it happens, we get a transmission spectrum for free, and actually I'm going to show you that first. So here we see the existing HST observations in the near infrared, very flat, and if we go out now to mid-infrared, the MIRI LRS phase curve of the transmission spectrum is also consistent with being flat out in the mid-infrared. So this transmission spectrum is really flat as a pancake, but this time, because we've stretched the wavelength range out to mid-infrared, clouds and hazes aren't enough to explain how flat this is. We additionally need to invoke a high metallicity atmosphere to flatten the observations. And for that, we need a metallicity of at least around 300 times solar, if we think of this as an N times solar atmosphere. Okay, now looking at the 3D information that we get from the phase curve and the temperature map, we found that GJ1240b is colder than you would expect compared to a 0 albedo temperature, which is shown in the dashed line here. This is temperature as a function of longitude. And this cold temperature shows us that bond albedo of GJ1240b is around 0.5. So this makes sense with the inference of clouds and hazes. This means that we have very reflective clouds and hazes. And on top of that, we find that the phase curve amplitude that's observed here is best fit by a high metallicity atmosphere of at least 100 times solar. So that actually matches very nicely with the transmission spectrum as well. So now let's look at the dayside and nightside emission spectra. And here on the left, this is for the dayside. For comparison, there's a black body spectrum in gray here, and for the night side on the right as well. These colored lines are GCM models run by Maria Steinruck and Piette. But I just want to focus on the comparison of these data points with the black body spectra to begin with. And these actually deviate from black body spectra by 3 sigma for the day side and 6 sigma for the night side. So before going any further, this is technically the first time that we've seen proof of gas phase absorption in this atmosphere, even though it's been observed so extensively. So that's really exciting that we know there's an atmosphere now. That's cool. Or we thought that would be. The next question is, if we have these deviations from a black body, what is causing these features? And what is the chemistry of the atmosphere? So we can start to look at that by applying atmospheric retrievals or inverse modeling to these data sets. And I very briefly showed this for the lava worlds, but effectively what we're doing here is fitting very fast parametric models of the atmosphere to the observations using Bayesian inference, in this case nested sampling. And what we get out at the end is posterior distributions for the abundances of different species in the atmosphere and also the temperature profile. So one thing I just want to highlight here is that usually for giant planets, we would assume in models that the background gas in the atmosphere is hydrogen and helium, which is a very good assumption to make for giant planets. But for sub-Neptunes and planets like GJ1240b, we can't make that assumption because it could be a steam atmosphere for all we know. So we tested 2 different assumptions. One is the usual one, where we assume that hydrogen and helium background, and the second one is using the centered log ratio parameterization for the abundances in the atmosphere. And this makes no prior assumption about which molecule is dominating, and instead you have identical priors for all of the species in the retrieval. So let's take a look at dayside first of all. So here is a very subtle absorption feature here, but there is a very slight one. And the retrieval is explaining this with water vapor absorption at the 2.5 sigma detection level. The reason that this is quite low is because there's a degeneracy between water vapor and methane. So we can't confidently distinguish the water vapor, but it is preferring it here. And then the retrieved water vapor abundances that we're getting here are a pretty broad range because it's not very tightly constrained by the emission spectrum, but it's around sort of 0.1 to 200 times solar, which does overlap with high metallicity requirements from the transmission spectrum and also the phase curve. We also tested retrievals with clouds as well, and we don't find any spectroscopic evidence for clouds in these retrievals, but that doesn't mean that they're not there. It just means that we're not seeing the features from them. And so instead, there might be other clues. There are hazes and clouds in this atmosphere, including the temperature profile we're retrieving here, which you might notice is relatively close to being isothermal. Indeed, that's probably why this feature is quite shallow. And so one thing that can result in pretty isothermal temperature profiles, besides that balance of opacities that I was talking about before, is the presence of hazes in the atmosphere. So these are some self-consistent models with different abundances of hazes in the atmosphere that we're doing for some follow-up work. And as you add more and more hazes in the atmosphere, you sort of get a more and more isothermal temperature profile. But at some point, when you add even more hazes, you get a thermal inversion. So this relatively isothermal temperature profile could be a hint of the presence of these hazes. So now moving on to the night side, we're seeing a very consistent picture. Here, the absorption feature is a lot more noticeable. But it's still a tentative detection of water vapor at 2.6 sigma, again, because of that degeneracy with methane. Once again, the retrieved abundance that we're getting for the water vapor is around 1 to 300 times solar, so consistent with the transmission spectrum and the phase curve, although it's not super constraining in itself. We still don't see any significant evidence for clouds in the retrievals, although again, that doesn't mean they're not there. And I think what's really interesting is that we're seeing completely consistent constraints between the day side and the night side, even though these are completely separate retrievals. So just another couple of tests to mention. I did mention before that we compared assuming a hydrogen-rich background versus making no assumption about the background composition of the gas. It turns out that that makes no difference to our results, so that's good that we're not too sensitive to that assumption. And just as an extra check, we also performed retrievals with a completely different framework. This is done by Jake Taylor using the Chimera framework. And for example, he used a different parameterization for the temperature profile, and we're still able to recover the same results as well. So we're pretty happy with the robustness of that. So for this, one of the first sub-Neptunes to have been observed with JWST, we've been able to measure the bond albedo of this planet, which can tell us about how reflective its clouds and hazes are. We've been able to get a really nice thermal emission spectrum, not only of the day side, but also the night side. And even though this has been a really mysterious, hazy planet, for which we haven't been able to get chemical information, we're finally starting to break through that in emission, and we're starting to get some clues about the chemistry of this atmosphere, which is really exciting. And I hope that this means that we will continue to get more constraints for other sub-Neptunes as well. And indeed, that has started to happen with other planets like K218b. But of course, here, I've mentioned the observations and the temperature profiles and chemical composition that we get from the retrievals, but really to loop this back also involves consideration of how the interior and the atmosphere are interacting to sort of self-consistently explain what we're seeing with these retrievals and observations. So for example, with the high metallicity that we're observing, one possibility is that we could indeed have a water world. Maybe we're seeing an almost pure steam atmosphere. That would explain the water vapor absorption and also the high metallicity. But on the other hand, we could be looking at a hydrogen-rich atmosphere that has lost a lot of hydrogen over time due to atmospheric escape, and that's resulted in a high metallicity atmosphere that includes water vapor, but also other constituents as well. And to distinguish those different scenarios, we are going to need to go back for more observations to test other sort of chemical traces with things like CO2, etc. Okay, so just to wrap up in the last few minutes, I'd like to talk about the future of the sub-Neptune landscape and a few things that I'm excited about. But I feel very lucky to be in this field right now because it's really the golden era at the moment of atmospheric characterization for exoplanets. I've talked mostly about JWST, but of course that's not the only instrument that's being used or will be used. We have Ariel coming up, the ELT, the GMT, and the VLT as well at the moment. And I just want to emphasize that there's a lot of synergy between what we can do from space at lower resolutions and from the ground at higher spectral resolutions. These different methods allow us to be sensitive to different chemical species in the atmosphere and different processes, which I'll touch on in a second. And with all of this wealth of data that's coming in, some of the science cases that I'm really excited about are, first of all, trying to distinguish the diversity of interior compositions of sub-Neptunes, as I mentioned before. For example, the difference between rocky or volatile rich interiors. Perhaps in the future, we can start to look at elemental ratios, for example, iron to magnesium ratios, things that we think about in geology and the Earth and the solar system, but perhaps we could start to do that for exoplanets as well. And this was in the context of a lava world where everything is evaporating. But if we go a little bit cooler, we can also learn a bit more about geology on exoplanets. So I'm thinking, for example, super Earths around 1000 Kelvin or so, where potentially we know some planets like LHS 3844b, which is this data point here, where we think it's a bare rock, that it's lost any of its atmosphere that it had due to atmospheric escape. And so emission observations of these bare rocks really are showing us emission from the surface itself. So this is a Spitzer point from Carnegie 2019, which is then compared to different geologies of the surface. Yes, this is just one data point, but with JWST, future instruments, we can make this more precise and also increase the wavelength coverage. Maybe start to remove some phase spaces we may not be able to precisely determine the geochemistry of these surfaces, but we can maybe rule a few things out. I think that's very exciting and brings us more to the regime of rocky planets like the Earth. And then finally, I also mentioned the synergy between high and low resolution. And so before, I was really talking about water vapor features and the CO2, but I kind of left out all of this rock vapor stuff, which you might have been wondering about. And these species are less easy to reach with thermal emission observations at low resolution because of the nature of their features and the wavelengths at which they appear. But some of these high spectrum resolution may be detectable. This is follow-up work that we're doing with collaborators in Oxford and James Webb. And because these have very dense forests of lines, we may be able to detect some of the rock vapor species as well as volatiles using the synergy between high and low resolution. And of course, these are all very specific processes of trying to learn about the interiors of these planets. But the bigger picture is that we need to understand the way that atmospheres and interiors interact, not only in the present day for an evolved planet, but also how that has evolved over time, because that's ultimately what determines the habitability of a planet like a super Earth or a rocky exoplanet. So for example, which gases are outgassing and ingassing early in the formation of the planet? Do volatiles get locked up in the iron core, or can they remain present in the mantle and on the surface? And how does atmospheric loss sort of modulate all of this as well? And so the science cases that I mentioned just before hopefully are a way to start to constrain a few aspects of this interior composition, but they really fit into this bigger picture where we need to also slot in atmospheric escape and evolution, and looking at younger planets to really track the diversity of planets throughout their different ages. So going back to this figure again now, I hope that as we build up these samples of observations and use these experiments in the sub-Neptune population, whether it's lava planets or young planets, that we could maybe start to answer these three questions and ultimately learn more about which of these planets could be habitable. I will leave up my summary there, and I'm very happy to take any questions.
Thank you, Anjali, for a really wonderful talk. A few questions online and in the room. If you're in the room, just raise your hand.
Really excellent talk. I was wondering if you have plans to merge these middle two topics and model some of the aerosols that could be in these lava world atmospheres.
Yeah, I think that'd be really interesting. And at the moment, on the photochemistry calculations, there are some aspects of that modeling that are missing, because normally when we think of photochemistry, we don't have like silicon in there as well. So I think that's a direction that needs to be expanded. And yeah, one example is, for some of these planets, if they have volatiles in the atmosphere, that would make it easier to sustain a global atmosphere. Then you could imagine something analogous actually to the hot Jupiters, where you could condense silicates on the night side and then carry over silicate clouds on the day side or something like that. So I think this is definitely something that needs to be looked at, absolutely.
Thanks for showing the nice JWST results. I was curious in the comparison, if you could bring it up again, the comparison with the HST, like they were obviously both flat.
Yeah.
But it looked like maybe the JWST wavelengths are giving a slightly smaller radius.
Yeah, so I think one thing to be aware of as well is like potential offsets between the different data sets. And so, yeah, in general, we found this to be the two combined to be best explained by these very flat high metallicity spectra. It would be interesting as we get more information. I think, yeah, we could actually go deeper in with transmission spectroscopy to try and see if any of the model of those bumps are just consistent with noise, but if we could try and go deeper with that, or at least go deeper in emission and then see how it compares to these bumps. Yeah.
Sure. And then on the phase curve, the correlation of offsets with metallicity, I gather that comes from GCM models. Do you know how that effect works, or?
Yeah. So basically, because there's a very strong or relatively strong contrast between the day and the night side temperature, or the night side is quite cool, we need a high metallicity to basically limit that horizontal redistribution. So one of the effects is just that you can you have a higher photosphere and you can radiate more quickly on the day side, so that energy doesn't get transported to the night side. There are deeper facets to that as well. That I'm not an expert in.
Just going back to that question, spectrum, you mentioned offsets. Did you actually test for an offset in these models, or did you just kind of take it at face value?
So we kind of took it at face value for this, and these are not retrievals; these are comparisons to forward models at this point. Yeah. So yeah, it would be interesting to look at that, but yeah, at the moment it's just kind of I don't know.
I have a question about that. With over 100 times the solar metallicity, and what could actually provide that such high metallicity, the source of it?
So first, I should give a caveat that we talk a lot about this like n times solar, and I think actually once it gets like 100, 300 times solar, that's probably not the right way to label it anymore. It's just out of convenience. So yeah, one way to get that would be if you preferentially use hydrogen over time, but leave behind the heavier elements through atmospheric loss. So that could result in an increased metallicity in the atmosphere.
So wouldn't that be quite common then? Because that process could be very common with this kind.
Yeah. So that would be interesting to test. And then, to be honest, I think it's also additionally complicated because you would expect, maybe you could expect some of those heavier elements to also escape, but then, for example, like carbon could escape more efficiently than oxygen. So that could also change those ratios. So yeah, there's a whole other avenue in that direction.
A question about GA1214b, actually 1214 star. So do you have an assessment of how stable the star in the spectrum is over tens of hours, for example?
So it was monitored from the ground, and it looked pretty stable from the observations. And yes, there were no signs of variability on the timescales of these observations.
But the ground-based precision is not quite what James Webb's precision is.
Yeah. So I don't know to what extent we can rule out variability, but yeah, it's a good question. I think we're relatively confident that it's not affecting this observation, but it would be interesting to check that. Yeah.
Does anyone online have any questions? Feel free to either raise your hand or put it in the chat.
Well, I have one more question.
Oh, yeah, go ahead.
Yeah, for the stellar activity and variability wise, do you have then UV or X-ray source? I mean, the variability study for this.
So I'm actually not super familiar with the follow-up that was done from the ground, so I'll have to look that up and get back to you.
Yeah, because if there's actually some episodic flare, obviously flaring star, then X-ray must have that data for that.
Yeah, that would be interesting.
Or if they don't, you could actually
Yeah.
take the spectra for that, because the flare could be very influential for that.
Yeah. So I've forgotten exactly what it was that was through the ground, but I can look that up.
Yeah.
Right. Yeah.
I actually had a question about the very tantalizing in prep you showed, where you start making the profile isothermal, assuming various phases. I'm just curious. So it looks like you're doing it as a function of the albedo.
So yeah, I should clarify. This is one little thing that I took out of another figure. So what I'm changing here is the haze production rate in the Karma models, and so these are the bond albedos corresponding to those different cases.
Okay.
And so the challenge is getting the right bond albedo without inducing a thermal version and emission spectrum. turns out it's actually quite challenging. So something I'd love to talk to you more about this as well. It could be composition dependent.
Yeah,
It's
so
the optical
that's my
Yeah.
question, like, is this just one composition that you then change?
This
the
one, yeah,
production
this one
rate?
is it's either thorns or this
The-
a more
the magic
reflective, yeah, the
reflective
mystery reflective ones. I forgot which one I put on the slide. I think this is the thorns. I also want to test the water-rich atmosphere
Yeah.
hazes. That's on my computer ready to run. Yeah, yeah. I think it's really interesting to think about the other optical properties that we could get, because if the atmosphere is very sensitive to that, or the spectrum is very sensitive, it would be good to know what parameter space we can expect.
Other questions? If not, give it another minute as people think, but if not, let's thank Anjali again.
I had a question.